Welcome to the last module of Day 10. I'm Amy, and I'll guide you through problems involving more permutations. Feel free to pause the presentation at any time. We saw in the last module that simple permutation problems tend to be straightforward. In this module, we will have a look at more complex permutation problems and tricks to solve some of these problems. For example, here we want to find out how many 5-letter words can be made from the letters C, O, U, and T if the word, say, has to end with a C, or if the word begins with a vowel. If the word ends with a C, this is the same as finding the number of ways the letters O, U, and T can be arranged. This is because the 5th letter is fixed and we can only arrange the remaining 4 letters. So the number of words ending with a C is 4 factorial, which equals to 24. How about if the word begins with a vowel? Since there are 2 vowels, O and U, we have to consider both cases. Suppose the word begins with an O, then there are 4 factorial ways to arrange the remaining letters. If the word begins with a U, there are 4 factorial ways to arrange the remaining letters. Now, since the word can begin with either O or U, by using the addition principle, we find that we can make 48 words that begin with a vowel. In the next example, we want to find out how many whole numbers are greater than 1,000 from 4 digits using 0, 1, 2, 3, 4, and 5. And how many of these begin with a 3. For the number to be greater than 1,000, it has to begin with either 1, 2, 3, 4, or 5. So there are 5 ways to choose the first digit. Since no repetition is allowed, the second digit will be chosen from the remaining 5 numbers. For the next digit, it's chosen from the 4 remaining numbers. And the last digit is chosen from the 3 remaining numbers. Thus, there are 5 times 5 times 4 times 3, which equals to 300 numbers. If the first digit is a 3, then it is guaranteed the number will be greater than 1,000. So the problem is the same as selecting 3 digits from 0, 1, 2, 4, and 5. So there are 5 times 4 times 3, which equals to 60 numbers beginning with a 3. Let's have a look at another example. How many even 4-digit numbers greater than 3,000 without repeated digits can be made from using 0, 3, 4, 5, and 6? This question is similar to the previous question, but with the added condition that the number has to be even. For the number to be even, the last digit must be 0, 4, or 6. If the last digit is 0, then we simply choose the other 3 digits from the remaining numbers. So there are 24 ways to do this. If the number ends with a 4, then the first digit has to be chosen from 3, 5, or 6 to ensure it is greater than 3,000. Then the remaining 2 digits can be chosen from the remaining numbers. So there are 3 times 3 times 2, or 12 ways to do this. The same argument applies when 6 is chosen as the last digit. So by adding them up, we find that in total there are 48 numbers. Okay, so let's have a look at next example. How many ways can Alice, Ben, Selena, Diana, Emily, Fred, and George line up if 1. Alice and Selena has to be together, Fred, George, and Ben have to be together, or Alice and Selena cannot be together? If Alice and Selena are together, we can consider them as one person and permute the 6 people. We also then have to consider that Alice and Selena can also line up in 2 different ways. So in total, there are 6 factorial times 2 factorial, which equals to 1,440 ways. For the next part, we can consider Fred, George, and Ben as one and permute 5 people. Fred, George, and Ben can also line up in 3 factorial different ways when they are together, so in total there are 5 factorial times 3 factorial, which equals to 720 ways. For the last part, we need to find the total number of ways 7 people can line up. That is 7 factorial, or 5040. The number of ways Alice and Selena are not together is the same as the total number of ways they all line up minus the number of ways Alice and Selena are together, which we found in the first part of the question. Therefore, there are 5040 minus 1440, which equals to 3600 ways they can all line up with Alice and Selena separated. In the next example, we want to find the number of ways we can display 5 flags on 2 masts. We know that there are 5 factorial ways we can permute the flags. Now we have to work out how to separate them to 2 masts. Suppose we use an X to represent a flag and a dash to represent a separator, such that everything on the left of the dash is the first mast and anything on the right is the second mast. For example, XX-XXX means that there are 2 flags on the first mast and 3 on the second. There are 6 ways to place this separator as shown below. Thus, there are 6 times 5 factorial ways to display 5 different flags on 2 different masts.